Hi everyone, Rabi here from RKALC. Today I'm presenting on the STM Studio, which is our general purpose environment for developing, analyzing, and designing strut-and-tie models. The main idea behind it is simple, which is rather than having an Excel sheet for one particular structural system, a core bill, maybe pile cap or a deep beam, STM Studio can give the engineer the environment where you can actually model virtually anything that you can imagine. So rather than showing the software features, I would be going through an actual structural problem, a real life or virtual life example that we can show the software capabilities and the limits. So at the end of this tutorial, we will be having this outrigger wall modeled and designed to the Australian standard for a tall building. So I'll crack on the problem itself. So we have a tall building, slender building that is 27 by 27 office floor, 45 stories, where you've got the aspect ratio of this building at 5.5. The wind load on this building probably will be governing the design. I will explain this later, but in this beginning of the model, we'll be talking about the overturning moments, the gravity system, the lateral system, and deformations, and we'll justify why an outrigger wall is required for a building of this nature. The outrigger system itself is a connection between the central core and the external columns, where you can increase the lever arm of your core essentially and add muscles to your system, where you can reduce the lateral deformation and the bending moment by extension to the core and spread it to the columns. The building in question is 27 by 27, as we mentioned, modular kind of arrangement. We've got 9 by 9 cells, and in the middle you've got a core, the black one there. The slab system is post tension with 240 thickness. That is derived by a span to depth ratio of roughly 35 to 40. Therefore, you've got 6 kPa on weight plus 3 kPa live load for office, if you're referring to 1170 standard, and SDL, let's call it 2 kPa. So that brings the total ultimate loading at 14.1 kPa and the service loading at 11, and the service loading multiplied by the area of the building or area of the floor gives you the mass. I'm adding 25% here to account for the lateral system and columns, because for taller buildings, this becomes more pronounced. I'll explain why I'm talking about the mass of the building in a bit. Typical column size is 1.2 by 1.2. You can work this out by having a tributary area of the column multiplied by the kPa by number of stories. So you'll get 26 meganewton, and you can size it up by 75% of the squash load, because the column is a stocky essentially. You can use RKALC concrete calculator to size up the columns. Now, the lateral system, as we mentioned before, the building is slender. So if we are talking about the behavior under lateral loads, it will be more pronounced at wind. It will actually pronounce totally as a wind-governed design for the building, especially the drift that where you size the building for that. The Holmes graph here is showing if your building period is in a space of above 5 seconds or 4 seconds, the wind response will be way higher than earthquake response. Although we might be thinking the opposite when it comes to the coupling beams because of overstrength design. Now, if I say that we've got 2.75 kPa average wind loading, which is by experience, you can work it out by summing the pressure factors, 0.8 and 0.5, front and back of the building, multiplied by the basic wind pressure. And then because of the MZ-cat, which is the high related factor, the wind loading becomes at this much. And if you do that, 2.75 times 27, which is the width of the building, you get 75 kilonewton per linear meter line load, and that results into 0.9 giganewton overturning moment. Is a decent overturning moment. Now, if you want to be really close to reality, you need to account for the crosswind effects, because the building is very flexural, very bendy, with a period of 6 seconds, because usually the period of the building is height divided by 45 roughly, or number of stories divided by 10, and add probably 20% over that. We've got 46, 50 stories, call it. So we are starting from 5 seconds, and with that, you might be thinking, not with the cracking and effective inertias, you will be arriving at 6 seconds service wind, which is sensible for a building like this. So if you insert in our wind calculator the period and the story mass, which is something that I've already mentioned before, you will get the crosswind loads, and you don't need to go to your client and ask for a desktop wind study if you're starting a project early on. You can think of it as either you're starting a scheme design, or you're peer reviewing your colleague, or the example itself, you might be designing the outrigger right away. Now, the core size, you've got a 9 by 9. Thickness of the core is, I would estimate it as 600 for a building like this, because again, a rule of thumb, good rule of thumb, to have the number of stories times 10, you will get the core thickness roughly, and beef it up by 10, 15%. And then the core inertia becomes at 238 if you just do BH to the power 3 divided by 12. Now, the core footprint is roughly 10% of the total floor, and that is not enough for a building of that nature. Probably you will require 15 to 18% to get the working core without any problem. So, and that can be proven easily by just like doing the overturning, or like calculate the lateral deflection, WH to the power 4 divided by 8EI free cantilever. You will get 608 millimeter lateral deflection, assuming the full inertia of the building is in action. But for ultimate, let's call it 60%. Some people say 80, some people say 40, depending on the cracking or how much tension you've got at the base of the core. So that will be like 1 meter lateral deflection, which is outrageous. By all means, you won't be accepting this. And if you're working on lateral deformation on serviceability, let's crack the core at 80%, and let's apply service wind pressure at, let's say, 65% of the ultimate for 10-year return period. You'll get H upon 300, which is again not enough. I would always target H upon 400 for total drift for a building, because of so many things that we don't have a room at this junction to talk about it. But H upon 400 is a good start as an overall drift, not interstory drift. Therefore, we need an outrigger. So I've replicated this hand calculation on FECALC, our general purpose finite element analysis program. So it shows again the same deformation as 608. And if I add an outrigger at circa 55% of the height, there you will get, which is essentially the most optimum location for the outrigger in a building where it works the most. And the axial area as well that is attached to that outrigger will increase the efficiency. So you'll get deflection is reduced to roughly half of what we are talking about, and that will lead directly to a good performing building. So we're looking at the metrics there. The outrigger here is going to be subject to 63 giganewton, and it is by nature reducing the base moment on the core by 30% roughly, and converting it to push-pull on the external columns. The shear on the outrigger itself here, if I just work it out, it becomes like 7,000 divided by the section of outrigger. We've got here 600 wide, same thickness of the core, by 6 meter deep. You will get 2.37 MPa, which is a good, very good number, not over design, not under design for outrigger. And that is our scheme designed for the outrigger that we will look at through the STM Studio. So now, before I start modeling the whole thing, I'll show you the end product at the end of the day. Well, after I've saved all of the nodes, the struts, ties, and the whole thing, you will get a report generated by the software that will tell you what the model is, how many nodes, thickness, struts and ties, etc. And will tell you that everything is pass, which is the end result. So you'll get a detailed report for all of the strut bursting, stress checks and similar, as well as for reinforcement where you've got ties, and the nodes themselves where you've got normal 3 face nodes that are CCC, CTT, CCT to the Australian standard, plus those general nodes, which is a novel method of calculating the stresses using sophisticated math that is published and verified by RKALC separately. That is what we have now. So we'll start modeling. I'll delete this. And then you start on a new domain. So starting on a new domain, the width of the core wall is, I just enable ortho there, click on this one. Width of the core wall is now meters, so go 9, whatever distance there, and another 9. And then the height of the wall, start with 6 meters. And again, 9. You can go here, double click. So this is our domain. And then we'll apply the loads onto this domain. So you don't have X, so minus, I'll apply half of the load at the top and half of the load at the bottom. Width of the column is 1200, as I mentioned. Another there, 0, minus 3600, Y direction, 1200, and then say OK. And then I put a support here, call it 1200 wide, and another support here, another 1200 wide. So that is our domain and loads. So here you've got a very cool feature, which is a TopoKALC, topology optimization software. It will first guess the load path that you will have within that domain. So by clicking on this Mitchell truss, you will see what is the possible or the most optimum load path, which is making sense. You've got tension there at the back, and you've got compression goes there. So that is an X kind of arrangement. And you can have here tension here at the back, and you have a tie at this location. I'll have a normal model of X and X arrangement for starters. So this is what I'm gonna do. So you just start by doing nodes, just throw nodes wherever you want to, and then pick up the supports with the nodes, put them inside of the domain, because the software will essentially start with the nodes only on the surface of the domain. Now you can bring them inside of the domain, and we need that actually because of the width of the struts and the ties. They should be fully included. And then click on element there. So you will be connecting the dots, literally. And then that represents the tension, that represents compression. The sky's the limit. You can use whatever load path that comes to your mind. And then click on Analyze. So you will start with the initial strut-and-tie model. I'll turn off the TopoKALC layer. You can turn off whatever layer that you want. If you don't want to look at the concrete, you don't want to look at the analytical truss, but we'll start with the provisional nodes that the software essentially start with. You've got node, for example, that node there. You've got a three-face node. So you've got strut that is perpendicular to this face, and the tie associated face will be at the back of the node because the tie usually develops from behind the node. So that is the literature. So you don't need to think about it much because the software is doing it for you. You've got a node like this one, very weird, non-standard node. So there is a tie there connected to this face, and you've got a tie connected to that face. You've got another strut going this way, and this tie is associated with that face. So you see how this one is looking like. So let's look at this node, for example. Just you need to double click on the node, and then review the properties, construct nodes, essentially. So this is what you get. This is the properties menu there. I'll just do it again. If you're concerned about node number 5, go node number 5. And then go to properties and construct node, or if you want to, just double click on it. So you'll get the node. So this is what we have. So that is the truss there, associated ties, and this is the blow up image of the node. You can make it as big as you want. So you look at it and understand this dialogue. So what we have, you have a strut there, which is this one. You have a tie, which is, if I just like do that, see the tie face, which is tie number S11 that connects to node number 4. This is what it says here. You just play with it until you get the node. So now this is 1, 2, 3, 4, 5 face node. So Australian standard doesn't cover those general nodes. So it will be your call as engineer to set the limit. I've here nominated 65 MPa and 600 thickness for the model. So if I say the CTT node is 0.6 beta factor times 0.95 times 65 MPa, you'll get something like, I don't know, 30 MPa. Let me even go less than that. If I just go with the calculator, it's 0.6 times 65 times 0.9. It's 35 MPa for CTT. let us just set a very harsh limit for us at, I don't know, 185 MPa there. And then what you'll see there on this node, this is a heat map for the compression stress within the node. And you can see there is a load there on this tie. Is you can just turn off the member names. So you can see you've got here a load of 7,000 applied onto that. 7,000 applied into that node there. And let me just see this face there. You've got the load 7,500 from number 11. And you will see the stress that is normal plus the shear stress, because the line here is not perpendicular. It's not hydrostatic because I start playing with it. So it will change the angle of that as long as you're testing. So what is happening there? The node total stress within the node is 15.3, which is the average between those nodes in a novel way. There is a whole publication issued by RKALC for you to go through it, because we don't like black boxes. It's all glass box. You can look at it. But just now, let me walk you through what is happening on this one. You select the node face, so it will tell you what's happening there. And you've got that is the member associated with it. If you want it to, that face to be hydrostatic, you just click on that. So you get this is now totally vertical on this one. If I want to do that as hydrostatic as well, so nothing will, so you've got one here and one there, and make that hydrostatic, and make that hydrostatic face, and that will be hydrostatic face. So this is what this software usually starts with. So this is what we've started with, but we don't want hydrostatic nodes, because although it's very convenient for the calculation, I don't think you will survive with any model with hydrostatic, because the node will be a dinosaur essentially. So what I will do, I will be just trying to save this node. So I've set a limit of 25 MPa. My stress within the node is 12. You can look at tension. If there is a tension, for example, a tie that is not applied here will be applied on the tie side. You will get tension. You will look at the shear. You see the shear. How is it changing in real time? The calculation will show you what is the shear within the node. If you want a sigma x, a plane stress converted to more circle for each of those triangles associated with those, and then we calculate the center of all of those, and then we work out the stress uniformity within the node. So you will see how it looks like when we finish. But let me just go with the principle, and then 13 MPa. So let me squeeze that surface, and that surface. So you see what's happening? We are within this 15 MPa. While I'm doing this, I'll make that perpendicular and that perpendicular, because it looks like very easy from here. And this face is perpendicular. And that one as well, where you've got the strut, make it perpendicular. Now we finish. Node is passed. Freeze and save. Close. Now this is a real node, not a provisional node. I'll repeat the process and expedite the screen for you to see what I'm doing nicely. So now all of the nodes have been checked, and they are all good. Now let's look at the ties. I'll turn off the analytical truss, and I'll show you something. We call it the offset truss there. Offset truss is downstream kind of truss, because the analytical truss is associated with the idealized nodes, the dot nodes, that we are not really concerned with when we are talking about strut-and-tie model, because you are talking about a bigger node. So look at this graph there, how beautiful. You'll look at strut pressing against this one, tie, which is representing reinforcement that need to be developed past the node, pressing on this one, and this is pressing on that surface, and this is pressing on that surface. So you'll find like the difference between forces is essentially a projection of the loading between the analytical truss. So you've got here 6459, which is the analytical, but offset truss is 6452. So there will be differences between those forces resolved within the node, essentially, to construct the nodes. This is what we would usually do for a strut-and-tie model, because within the node itself there is here equilibrium, and you work it out, and then you work out then the revised strut-and-tie model, a classical problem. Now I'll turn off all of those, and then I look at the struts. So we've got 1, 2, 3, 4, 5 struts. So let's look at this strut. Double click it. You need to insert the service load there. If I've got 8,000 divided by 1.3 to get the service becomes 6,200, say. And we look at the strut. What is happening there? The stress in the strut is exceeded 22 MPa. And the design stress is 13 MPa. So let's see what's wrong with that strut. Looks like this one is highly stressed, or this one is highly stressed. So look at it again. Double click on this node. Now let's see the strut there is 22 MPa, which is way more than what we'll be expecting. So what would I do there? I'll make that bigger. Unlock the node. I'll make that way bigger, way bigger. Still maintain it to be hydrostatic phase there, but this is not hydrostatic anymore. And then the stress has reduced to 17 MPa. Probably we'll need a bit more than that. So I'll make the node to grow more to be proportionate to the loads. So what you're getting there, let me make that hydrostatic as much as I can, make it hydrostatic. So we got 11 MPa here, 14, 15, 14, and 11. So it looks fine as a node. And then the node is working 90%. Now we look at the strut again, double click it. So just do that and put the SLS force for this strut. Now it's because we changed the node size, so the truss forces have changed from 8,000 in the previous pass. It is now 7,500. 74 divided by 1.3, get 5,720. And now it says the reinforcement needs to be checked. So auto size the reinforcement, so it'll give you the bursting reinforcement for this one. Now we are done with this strut. Let's look at that strut. Just insert the loading there. 6.2, so 8,000 divided by 1.3 is correct there. Now click on this one. See, you've got here an issue. The angle between the strut and the tie is 29, which is not 30 degrees as per the Australian standard. So what do we do there? We need to stretch it again. So I'll change the inclination of this by working on this node again. Just take it all the way down, work it out, double click on the strut. Now you've got slightly increase in the stress, and this is probably because of this surface there. Unlock, increase that size, freeze, double click. We're getting close. So maybe this surface here. Yeah, make it bigger. Check. The angle again is not working, and that is the iteration that we need to keep doing. So let's increase the depth of the whole thing. Save it. Now the strut is working. Congrats. Next one. Working. But you need to put the service load 53 divided by 1.3, 4075. No bursting required. Everything is fine. Next one. SLS bursting is working. Nice there. Let's look at this. So you've got this strut here is failing because of the angle is less than 30. So what do we do there? Because this is the only thing I can do within this geometry. If I bring this one here, so that will fail. If I bring that one there, so this is suggesting that this model doesn't really work. So it needs a bit of love. And how would we do it? So what is the height of the outrigger? From here to there is 6. And if I want to save it, I need to get probably a bit more height. And this is making sense. So if I just take that, make my structure slightly bigger, and that would be the call that you will make as a structural engineer. And then increase the truss size. And does this look like 29 here? So we need to bring that slightly in. Bring that slightly in. 29 still. Now everything is working. 67 divided by 1.3 is 5200 service load. Strut is working like a dream. Now this one is working. This one, okay, this one is as well working. Now we just because we've stretched all of the nodes and the strut size, we just need to reconfirm the nodes so you'll get that green tick activated. Double click on each node, unblock and block. So you need to put the limit for those non-standard nodes just to make sure they are all pass. All pass. This one is pass, all pass. That one, what's happening here? 24 pass. Pass. Now this strut here, the bursting zone is going outside of the domain, which doesn't make sense. Then we can change the strut to be prismatic, and then we see, and it should be working because you can confine this area without any problem. Now, if I want to look at the reinforcement, just turn on this toggle. So it will tell you how much reinforcement you've got. So double click on any reinforcement, change the diameter, and it will tell you how much you need right away by working out the loads. So that is the whole thing that we've been working on a lot. So change the analytical truss view. You start from wherever you want to start. So we are here, analytical truss, offset truss, together with nodal zones. And now report, if I just go to the report, there is a bit of check here. Where do you have check? Some struts, they need to be rechecked again. Anything here? All good. Just finish them one after the other. Report. Yeah, this strut here needs a bit of work. Strut number 7. So where is strut number 7? Is this one here? It needs, yeah, that to be working. And then at the end of the day, everything has worked. And you can generate this report and add it to your library. Just a few nodes there. When you have reinforcement, you need to develop that reinforcement past the node. So if you've got a lot of reinforcement needed for a special element like this, I'd recommend to go with the frizzy bar or McAlloy with the end plates on the opposite side of the node. For strut bursting reinforcement, that skin reinforcement that you're adding to your wall would be more than enough. If you're very curious about the theory, look at our published note there, which is this one there. If you click on this one, you'll see the theory behind the node stress calculation, which is not very new. It has been used by CAS and Strut-and-Tie, but all of those are Windows-based applications and pretty old. With RKALC, we bring in a modern and nice way to present it. This concludes the example. Thanks for watching.